I list a bunch of people here because the talk is based on collaborations with them and also work done independently by other researchers. There is more work, of course, and there are other researchers, but this is a reasonable set of what I base my presentation on. So Felipe is one of my students who is somewhere over there in the audience. Luismi is also doing work with me on stream runtime verification, but I will not be talking about his work. So let me see, there we go. All right, so what's the main goal of stream runtime verification? The main idea is to express rich monitors easily. So in the context of my talk, runtime verification is a technique to do dynamic analysis based on generating monitors from formal specifications. I mean, this is a general statement. There are many work of different flavors that have been doing this, but stream runtime verification, I would claim, is convenient because it allows you to express very rich monitors, to collect very rich verdicts, and is humanly appealing as a formalism. So maybe you remember this taxonomy figure from Martin Leuke's talk the other day. So I will briefly give some context of where in this landscape stream runtime verification is. So let's begin. In terms of traces, runtime verification is a technique to express properties of finite traces. One may claim that finite non-completed traces would be as well, but definitely at least the standard work on stream runtime verification is not intended for infinite traces. One could claim that you're doing dynamic analysis, so all you can hope for is to see a finite trace anyway. In terms of the integration with the system, this is an important point. Stream runtime verification is meant to be outline. Those of you that attended Chris's talk yesterday, he was talking about aspect J, how to inline monitors in the code. So you have your code, you have your specification, and you generate a modification of the code that is supposed to behave as much as possible in the same way, but has the monitors inlined in the code. So in stream runtime verification, the technique is outline, which means that the monitor runs completely independently from the code. In terms of the stage, stream runtime verification can be used both for inline and for offline. So inline means that the monitor runs alongside the code. Yes? Online. So it runs online, meaning that the monitor runs alongside the system, still outline, because you have some infrastructure that allows you to run the monitor alongside the system. And it can also be used offline for postmortem analysis. So when you have a dump of logs and you want to analyze them. In terms of the interference with the system, it's meant to be non-invasive as much as possible. So of course, to do non-invasive runtime verification, typically you use an outline monitor because it's very difficult to be non-invasive if you change the code itself. All right. It's meant to be just monitoring technique. So if you want to build some reflection and act upon the system, for example, to do enforcement, of course you can build it on top, but the technique I will be talking about today is just passive, meaning that you just observe the system. You don't act upon it. It's debatable whether it's state sequence or event sequence, because for the synchronous runtime verification, which is a classical stream runtime verification, I'll be talking about most of the talk, is mostly state-based, even though for the asynchronous or real-time is more event-based. All right, and the area of application is beyond safety checking. So that's one of the important points. One of the takeaway messages is that you can collect very rich information about your traces, not just yes-no verdicts. All right, so back to the main goal. So we want to express very expressive monitors that extend the monitoring beyond yes-no. We just don't want yes-no verdicts, we want richer verdicts, finer grained verdicts. And it's user-friendly, even though this is less, it's more difficult to sustain scientifically. We'll have to do studies, but in our experience, shared by Martin Leuker and Ben Fimbiner and others, they've worked with companies offering different formalisms they prefer to use something like what I will be presenting today rather than temporal logics, mu calculus, and so on, which is great for scientific studies, maybe as low-level formalisms, but it's very difficult to convince engineers to use these other formalisms. So let me start with an example. This property, which is a modified LTL property. By the way, who is somewhat familiar with LTL here? Or better put, who is not familiar at all with LTL? Excellent. Okay, so this property essentially states that f holds with probability at least p in a given trace. It's a non-standard LTL property, and this was suggested in a paper in Runtime Verification some time ago in a tool called Eagle, and this is the solution they provided in the same paper. So let's try to shed some light into what this is supposed to mean. So you have here somehow like a template or a function A, which has 4 parameters. One of them is the formula you're checking. Another one is the probability you're checking, which is passed in the recursive calls, both of them. Then F, which I understand that it intends to count the number of times not F happens, and T, which I believe it counts the number of steps in the trace. So if the step is final, meaning if you're in the final step of the trace, then you do this part here. In case you have an F, you don't count in F, you never count in T because this is the last point, and you check against the probability. In the case you're not at the end of the trace, then you add 1, and you add 1 to F if you don't see the formula F in that position. Well, even after my wonderful explanation of what this means, you probably agree that this is not a very palatable way to express a relatively simple property that an engineer would like to express. So even though I haven't introduced syntax, semantics, and so on, this is more or less how it looks in stream runtime verification. So you express one stream that counts the T, the number of events in the trace. You count the Fs or the not Fs. It doesn't make much of a difference. And then you just have the division compared with P. Engineers prefer to write things like this than to start thinking about things like this. Again, to sustain this formally, you will have to do a study, but I hope to convince you that in terms of how easy it is to understand, this is closer to a programming language. Engineers are more familiar with programming languages than typically with logics and so on. Well, a little bit briefly of story. It all started in 2005. Of course, it's based on previous work. One can claim that it's similar to synchronous programming languages and so on, which is true. But the first paper in the runtime verification context was this Lola paper. When I talk today about stream runtime verification, I mostly mean Lola, which I did with Bernd and other people when we were graduate students not so long ago. So essentially, the main idea is a collaboration with Synopsys, which was a verification company. And they had synchronous circuits, and they wanted to check the traces they generated, essentially. We proposed to use LTL, but they wanted something easier to use and something where they could extract more information from the traces. A little bit later, Pinueli and Sack published a paper that has been quite influential on testers, which essentially translate temporal logics and richer temporal logics into circuits where the signals, or say the wires in the circuits, represent the streams of Boolean values that flow, which is more or less a similar idea than what you do in stream runtime verification, even though they were limited to Boolean signals or wires. And in our original paper, the main idea was that you can generalize to compute other values. Later on, there's been work at NASA by Christine Rossier and also by Lipike and so on using similar techniques to monitor different aspects of the vehicles at NASA. And more recently, the group of Benfin Biner and his students have been working on extensions of the original Lola formalism for different purposes with different additions that are necessary for those purposes, like networking and aerial vehicles and so on. This is a theoretical work. If I have time, I will be presenting some comparison between streams and finite automata in terms of expressivity, complexity, and so on, which I believe that partly explains why this formalism is very convenient, because it's very rich. All right, and more recently, I have a collaboration with a group of Martin Leuke and his students, where the main idea is to debug and test multi-cores based on runtime verification in a non-intrusive way. So they use debugging capabilities of modern multi-core chip processors to extract signals, and externally they use FPGAs to monitor online the signals extracted. So here you can see how it's outlined and it's non-intrusive, because the chips are already producing those signals for debugging anyway, without influencing at all the execution of the program. So the intention here is to do low-level concurrent multi-core testing. All right, so some motivation. Consider the following formula in LTL, always P. If you unroll it, and allow me to introduce a little bit of the syntax of string runtime verification, you can claim that the solution at a certain position depends on whether P happens at that position and whether what you're computing, which is the specification, happens at the next position. And you can claim that if you fall off the trace, I need to give a value, say, for example, true. Okay? Another way to, so another formula could be, for example, whether P held in the past at all positions, which similarly can be expressed by the unfolding. These unfoldings are quite common in LTL, but if you use the unfoldings, you can give names to the wires, to the solutions at every position. So this formula at some position can be determined by the property, state property, for example, that you're checking, and whether the same held in the previous state. And of course, if you go to the beginning of a trace, you have to start with true. And similarly, you can do eventually, once in the past, but of course changing ands by ors and trues by false. And you can do until, and so on. Yes? Okay, so I will give the precise descriptions later on, but this is a shift. So S depends on S in the next, or in +1. And this is where you say what happens when you don't have anything more to see. Because this is finite traces. So you need to give a value when you fall off the trace. All right, so until and wait for, the only difference is obviously the default value. In until you really want to see Q. In wait for, it's fine if you don't, as long as you see P. And of course, next is the easiest one. This is, if you want the strict next, you need to have a P, and you need to have a next. Otherwise, you say false. The weaker version of next would be just having a true here. So one could use something like this to express your temporal operators. But even more importantly, what is it that you're doing to compute box P in a given state? What's the steps you're taking? You're just fetching values of P and fetching values of S, and you're computing a single step operation. So what stops you from performing a different operation on the same algorithm, on the same dependencies? So why restrict yourself to Booleans? Because if you don't, you, for example, could count the number of P's, as we did in the previous example, just by switching and by plus. So the main idea is to separate the two aspects. One is the algorithm, essentially the dependencies between these values that you fetch and the individual operations that you perform. Once you separate that, you can work on each of them independently in the language you're designing. So for example, let's say once P, if you wanted to evaluate once P at point in a trace in LTL, what you have to do, for example, imagine that P holds in this state and in that state, what you have to do is to go backwards, trying to see a P. So once P holds here, if either P holds here, which unfortunately it doesn't, so you have to check once P here and check P, it doesn't, so you have to check once P here, again you enroll and you have the P, you're happy, you determine true. Okay? So in terms of, say, the pseudo string runtime verification specification, you have these values that you may want to check. to fetch. So to check the value of once p in this position is to check the value of the stream s, which determines the specification at that position, which may need the value of p or the value of s in the previous position, and so on. And in this position, you have a true, because that's the assumption on the trace. So you compute a true. This is an explicit representation of the values you need to fetch, if you want to see it this way. All right. If, for example, p doesn't happen at all, what once p would do is that it will go one step at a time until it has no more steps to go back to. So it will determine false. That's the semantics of once p if we write them down, obviously. But this is the algorithm that you have to run to check once p. In the same way, if you want to see the string runtime verification, you will have to go backwards all the way and then use the default value. What the question was before is, say, the non-standard decision that you need to take on finite traces. Yes? Yes, you are, and I would like to ask you to be patient, because this is what 90% of the talk is all about. All right. So let me talk about domains, which is the other part, the data. Well, in LTL it's simple. The only domain there is Booleans. But we consider richer domains. So our domains are essentially, first of all, the theories. Well, all functions are interpreted. That means that you have, for example, the symbol OR to build Boolean expressions, Boolean terms. But you also have an evaluator for OR if you happen to have values on both sides. So it's not uninterpreted first of the logic, it's interpreted first of the logic, the domains we use. And we also require that we have anything else because it's very convenient for runtime verification. I'll give you examples now. So first thing is sorted first of the logic, so all terms are typed. So variables have a type, for example, and all functions have a type of the arguments and build a term of the given type of the term you build, and all functions are interpreted. Let me give you examples. This will be easier to explain this way. So Booleans, for example, the only sort that we use is bool. The only constants are true and false, which are of type bool, and they have a meaning once you give meaning to the functions. So for example, x and true or y, where x and y are variables of sort bool, is a term of sort bool. So in our context, this will be used to represent stuff you don't know, but you know it's bool, and you know the relation between the elements in the formula. And of course, you can do evaluations. So for example, if you have this formula, and x happens to be true, y happens to be true, y happens to be false, true is true, this is what you have to evaluate. Now you use the evaluation of these functions, and obviously you compute true, as you see there. So this is syntax, typed, and this is an evaluation applying the interpreted functions. So more interestingly, you can go to bool 3, which Martin explained the other day. So you have 3 constants. You have true, you have false, and you have this I don't know, which is used to interpret I don't know this value. And of course, you have all the Boolean functions. You also have if then else, where the if is a bool. So if something, then either this expression or that expression. So for example, we can evaluate now the same term, but instead of true, let's say I have I don't know, we can evaluate here I don't know, and f is I don't know, true, and so I don't know, or f is I don't know, true, and I don't know is I don't know. This would be an evaluation. We can also have, for example, bool 4, where now we have it's likely that it's true, it's likely that it's false, and we will have evaluations in the same way. We'll have this as constants and also as values. All right? Of course, we can have integers. I add Booleans because we have anything else. In the integers, we have all the values of the integers as constants. We have operations between the integers, the usual ones. We have predicates that produce Booleans. And we have the if then else. So for example, x plus 3 minus y is one of the terms you can build in this interpreted theory. And a simple evaluation of this term, once you know these values of these variables, would be as I present here. So if 7 is less than or equal to 3, that's false, so you have this term. 3 plus 1 is 4. This is what you produce by evaluating this. Because I happen to know how to evaluate less than, plus, and if then else. Okay? Of course, you can have even richer sets, even richer theories, even theories that you can program, ideally, when you build a string runtime verification framework. So, for example, you could have elements. You could have, finite sets. So you could have empty as a set, singleton sets, membership, and so on. This is very easy to implement in your programming language and to implement such a domain. So, for example, if you want to evaluate if 2 is in this set, then I remove it. Else, I give you the empty set, which 2 happens to be in this set. By the way, this is just this term when you instantiate the variables of type set for the values I give here. Then you obtain 1, 3. Okay? So you can see that this looks a way like a programming language. If I ask you the task to implement such a domain, you would probably sit down and implement it easily in your favorite language. Okay, so one important point that I want to remark is also simplifications. In runtime verification, this really gives you a lot of leverage in terms of performance. So sometimes you have a term, and you don't know the values. So you cannot use directly your interpreted function to obtain a value as a result. But sometimes you can give an outcome, a definite outcome. So let me give you an example here. If you have an if then else, obviously, and you know the value of one branch, you don't really need all the values of the variables, because you know that since you have a true in the if, the outcome is 17. You just don't have to wait for those. So you can anticipate, okay? So for example, if you remember the unrolling of the ones, of course, once you have the left-hand side as a true, and you have an or, you don't have to wait for the right-hand side. So you don't have to keep searching for the p because you just saw the p. But in terms of how you do the evaluations, you will have a term with a variable on the right-hand side that happens to have a true on the left-hand side connected with an or. So you use the simplification, something like this, right? And you would simplify. Well, in this case, it would be, say, x or true, and you will have to true. So we capture the simplifications typically in string runtime verification as a collection of useful rewrite rules in your domains. Question to the audience: can we aim at perfect simplifiers? A simplifier that if a term can be simplified to something, then you have the simplifier that does the job for you. Okay, let's begin with Booleans. If I have Booleans, can I aim to have a perfect simplifier? We can easily see that you would need to solve a SAT query. Just to know whether a term that has many variables can be simplified to true is just a validity check. If it can be simplified to false, it's an unsatisfiability check. So you will have to have a SAT solver and solve an NP-hard problem, just for Booleans. For integers, I mean, you can imagine that is an undecidable problem, and we can craft or reduce your favorite undecidable problem into this. So no, we don't have perfect simplifiers, we just have useful simplifiers. Okay? So, for example, the if and else rules with false and true. It's one of them. All right. So one example, classical LTL response property, every request has a response. Well, that's your intention, but that's not really what the formula says. It's a compromise that we do in LTL to have a tractable way of doing something similar to the formula. Why it's not the same? Because you can have several responses for one request. You can wait for several requests and just give one response, and that would be fine for the formula. But this is not really what you mean. So how we do it is in string runtime verification with Booleans. So you can have a stream that essentially captures whether you have a response, either now or maybe later on, but of course I have a false. So I'm unrolling recursively, but if the trace finishes and I haven't seen a response, the value of f response now will be false. I agree with Gerardo that this depends on future, but semantically speaking, this is what you obtain now if you can unroll it, everything, okay? Of course, granted now means that if I have a request, then I eventually have a response. That means that the request I have now is either non-existent or it will have a response. Okay? And OK is whether I'm OK at all positions, meaning every request at every position will have a response later on. But you can do better in string runtime verification for the same informal specification. So, for example, you could count the number of requests and responses. So I could count adding 1 when I have a request, adding 1 when I have a response. And I just have to check whether at the end I have the same number of responses that I have as requests. So this last that I'm using is only true in the last state, which I can define. I can have it like natively in my language, or I can define it. Well, an additional sanity check one could say is that, this way you're checking that you have the same number of responses as requests, but what if the responses come before the requests? You can define or rule out that easily by having just these 2 lines, which you essentially check at every point that the number of responses is less than or equal to the number of requests. So I would defend that this specification is more truthful to your intention for that formula. Why people use LTL then? Well, because it's tractable. If you do model checking, you have to be effective. And this language will have an undecidable model checking problem, even for finite state cookie structures. But we're doing runtime verification here. We just have to evaluate on a single trace. So we can afford to go to richer languages. And in fact, one easy exercise is to do a rich embedding from your logic into streams and use your evaluation algorithm to check the LTL for free. And this is what I presented in this slide previously, because I translated every operator of LTL into just a 1-line specification that I can compose. All right. You can do even better than integers. You can have sets. So you can store in your sets the IDs of the requests, the IDs of the responses, and just remove them. Remove the actual responses that correspond to the actual requests. So if at the end of the trace your specification happens to be false, you can spit out the requests that have not been responded. This is much richer than just saying, hey, no, which is what you're doomed if you have a Boolean specification. All right, so another thing you can do, as Martin presented, is to use bool 3 or bool 4 to give slightly richer Boolean outcomes. So for example, instead of saying true when you have a box P, you could say, sorry, this should be top P, right? Sorry, that's a typo, but you get the idea. You unroll the piece. If you only see P's and you get to the end of the trace, you say, this is likely to be true. On the contrary, this should be bottom, sorry. If you want to see a P and you see it, you're definitely true. But if you don't see it and you fall off the trace, you say, this is likely to be false. I was expecting to see a P, I haven't seen it. It may happen in the future, I don't know. But so far, I haven't seen it. So you can say a bottom P. And this is essentially the Boolean for semantics for LTL for semantics. And you gain them here just by having the different default values in the fall-off moments of the trace. All right, let's go to the syntax. So a specification has inputs with their types. So you can have Booleans, integers, strings, sets. Every domain that you program, you can plug it in there. Yes, Elias. Well, this is an interesting question, but it's been explored only for some of the domains. So as I will, if I have time, present, if you restrict yourself to Booleans, you're complete with respect to regular languages. For other domains, I don't know. I'm pretty sure that you can get Turing complete easily with a rich enough domain. But this is an unsustained claim. I mean, we could do the work. It's not difficult if you have stacks or registers that you can use them to store all you need and encode a Turing machine. So just a conjecture. All right. So you have input strings. These correspond to the observations you make on the system. Then you have output, which are obviously typed. And then you have expressions that tell you how the output should be. With respect to the inputs, but that would be a bit boring if they only related to the inputs. So also with the other outputs and themselves. This should, I mean, for those computer scientists, this should flag like, hey, there is danger here going on. So I will explore it in a moment. And of course, you have triggers because your idea is that you report things to the user. So for example, when there is a violation detected, you report it to the user. So this is called independent stream variables. This is called dependent stream variables, which are the outputs and internal streams that you compute. And these are the defining equations of the dependent stream variables. So a defining equation can be built from constants of the domains. Of course, the constant will have the type of the constant in the domain. The streams will have the type that you declared. But this is one of the expressions that you can have here, just a stream. Functions applications with your interpreted functions that of course they have the types, given expressions of the proper types. This expression as a term will have the type declared in the domain. And you can have offsets. This is the interesting one. So you give it an expression and given a constant, an integer constant, and a default value. This is an expression of the type of the given expression and the constant which must coincide. Okay? So, example specifications. I have an output of type bool called OK, which is true at all positions. This is perhaps the most boring expression you can define, except false. Height, for example, you read an integer and then you just output it. It's a little bit less boring, but still quite boring. You can, for example, read an integer and Boolean and output OK and the integer, for example. Still quite boring. You can have, obviously, all the functions that you have in your domain for integers. You can do mod, you can do plus, square, etc. You can produce Boolean outcomes, integers, combining your Booleans and your values with the conditional, for example. You can combine your Booleans here and there and so on. Still boring. Now you can say, oh, I'm reading a Boolean, so I have in this stream the value of the Boolean that the system produces in the next state. This is something you can define. At least you can build this specification. And you can also have pref, for example, which is the value that you're reading in the previous state. You can, for example, have a specification that computes the parity. So it looks at the parity in previous state and it adds the in-bit modulo 2, for example. And you can have, this is, let's say, this is similar to a response property. So here we are unrolling OK with itself in the next state. So this is just to illustrate some of the syntactic specifications you can build. I haven't reached the semantics yet, so be patient. Now, normalized specifications, these are useful to reason about. What you restrict is your expressions here to be only constant or variables, only function symbols over variables, and only shifts over variables. Question, is this limiting your expressivity? Simple answer, no it isn't. Why? Because you can take your specification and introduce fresh new variables for all the terms that are offending, the terms that are not making your expression not flat. So here you have a plus symbol, but the left and right are not variables. So you can introduce one variable for the left-hand side, one variable for the right-hand side, and so on. And you transform this spec into a flat spec. So S here, so S1 and S2, which are fresh, obviously of the right types. S1 has this value, S2 has this. Now this is not flat again, so we introduce a new one. And then at the end of the day, I end up having a flat specification. So I need at most a linear number of fresh variables. This is not too bad, right? And it allows to do many proofs and many developments much more easily. For example, because you only have shifts on variables and not on expressions. But I hope that you get the idea that this is just a simple syntactic transformation. All right, semantics. This is the interesting point. So what's the intention of all this work? So far it's been, oh yeah, great work. Let's have domains, let's do rich stuff. But what's the purpose of this work? What do we want to do? Well, we want to build monitors. So you want to have spec, and you want to generate a monitor. That's the goal at the end of the day. We're doing runtime verification. And of course, at runtime, you want your monitor to read traces produced by your system and produce traces as output. This is what you want the monitor to do. So intrinsically, you want your monitor to be a function from inputs to outputs, right? I mean, probably this slide will work for any formalism. But in our particular case, we should have a compiler, the Lola compiler, for example, that takes a spec and gives you a monitor. So first, a couple of notions that I need to get to the semantics. So imagine that you have a specification with a bunch of typed, obviously, input streams, a bunch of output stream. Evaluation is evaluation of length n, is a stream of values of the domains, one for each stream, for example. Imagine that this is a Boolean stream variable, and this stream of length, I don't know, maybe 15, of Boolean values would be one valuation of size 15 for this input. This is one of the possible stream of values that you would read in practice at runtime. Imagine that T2 is integer, so you can read this 15 in sequence of integer values, and so on and so forth. And for the outputs, you can also claim, imagine that you have them. Just for the sake of argument, imagine that you have the candidate, the inputs and the candidate outputs. That's what we call evaluation of a specification, is candidates. So given those candidates, I can evaluate the semantics of every expression. Okay, so for example, what would be the semantics of a constant? Given the streams, what would the constant be? Okay, so the semantics of an expression is also a stream of the same length as all streams that are in my example. I mean, in my case. So all inputs are of length n. The semantics must give, for every expression, also stream of length n. So what would be the semantics of a constant? Anybody? This is the boring one. If you don't answer now, you will be answering the difficult ones. Yes? Sorry? So keep in mind that semantics must give you, for every expression, in particular for C, a stream of length n. You just have to fill all positions of that stream. So what do you fill in all positions? Somebody? Yes? The constant C. So, but if we write it mathematically, the semantics of C must be a lambda if you want, where you get the position from 1 to n, and what you output is just a constant. I mean, this is pretty obvious, right? What do you do for input variables? You just give the value given, right? You fetch it. So you have your tau, so your t corresponds to tau, t1 to tau1, you just fetch a value at the given position. And j must be a legal position, because this is a function from 1 to n into values. For outputs, this is a tricky one, but not that tricky. Think about it. So if you want to evaluate an output, and you presume you're given the output, you just fetch it. Your output is your candidate output. Okay? Because I have been given by an oracle the outputs. Okay? Or somehow I have the candidate output. For functions, very simple. You just evaluate the function under an interpret case into the recursive expressions. And for shifts, now I use only, because it's simpler, I use normalized. So I take only shifts of variables. What I do is that I fetch the value if the position plus the offset takes me still within the stream. If it takes me outside, then I take the default value. Yes? I don't understand the question. No. This is just a homomorphic. So when you want to evaluate the function and parameters, you evaluate the parameters and pass them to the function. That's what I mean here. It's just homomorphic evaluation. So the meaning of a function on streams is the application of the functions on the streams. That's the idea. Which essentially witnesses the idea of separating data from values. This is where you encode all the data, right, in your functions. Your or, your and, your plus, your less than. Okay? All right. No. This is just, if I'm giving valuations of the same length for every variable there is, input and output, then I can evaluate the expressions. This is what I've done so far. Tau is just a stream of values for an input variable. Sigma is a stream of values for an output variable. So it's just notation to convey the difference. Of course, our intention is to compute the sigmas, given the taus, but we're not there yet. This is pretty declarative if you want. You tell me a pair of input outputs, yeah, I'll check. Okay? So given spec, one thing we can do is evaluate the right-hand side, right, which gives you a stream of values, and try to match it against the left-hand side, which is the stream of values that the variable corresponds to. This may be matching or may not be matching. But say that it matches for every stream. The expression is the same as the stream. Obviously, this is extensional, so meaning for every position, this stream and this stream are equal. If it's the same, I say that this is an evaluation model. So far, it's quite declarative, and some runtime verification people that only read the papers up to here find it preposterous. Why? Because it's not telling you how to compute it. It's just telling you, you give me an input-output pair, and I check for you. Okay? This is a very prologue way of defining functions, if you want. You're saying what the good output is for the input. Give me the input-output, I'll check. So it's very denotational, if you want. Meaning that a specification is a checker for input-output pairs. So we're not there yet in the sense of runtime verification. All right. So we write it as usual. If you have the tuple of input, your tuple of outputs, these are values. These are valuations, candidate valuations. And we write this when they satisfy spec. So it's very relational, if you want. All right. So these semantics require the output. It's not independent of the output. If I don't have the output, then the semantics don't tell me anything. So for example, take this specification. If I give you this input, so essentially the output S is a Boolean and tells me whether 10 is less than or equal 10. So this output and this input as streams of length 12 is a model of the specification. In fact, I claim now without proof that this is the only output that extends this input to become a model. Okay? I mean, it's pretty easy to see, because if you give me a t, then there is only one thing that it can be. It's either smaller than or equal to 10 or it isn't. If I give you this, a bit more dangerous. I'm saying that the value of s is the value of s and 10 less than or equal t less than or equal 10. Well, now it's not so clear. If I give you this input and this output, well, it's a model. We can check whether s is the same as s and 10 t less than or equal 10. But this other stream, which is obviously different than this stream, is also a model. So now I have two pairs for the same input. Why? Because when t happens to be not less than or equal to 10, this is false. Sorry. Yeah. No, this is true. That's right. Okay, when t is less than or equal to 10, this is true. And then you're left with s equal s, and you can choose true or false. Both would work. So for this specification, there are some inputs for which you have two different outputs. So it's not functional. Okay? Let's take another one. This is a tough case, because you have to make s be a Boolean value that evaluates to the same value as not s. That's a bit more difficult if you think about it. You take an input for t, and there is no output possible, satisfying the equation. So sometimes you have exactly one output for every input. Sometimes you have more than one. Sometimes you have none. All right. So what's a well-defined specification? A well-defined specification is one such that for all input streams, there is a unique output stream that satisfies the spec. Namely, that your spec is functional. So how do you check well-definedness? In general, take integers, strings, stacks, counter machines. I'm giving clues here. This is an undecidable problem, obviously, and you can encode your favorite PCP, anything that you want into this. So this is the end of the story. Well, this is pretty bad. I give you spec, you don't know whether before you even start thinking about an algorithm to monitor it, you cannot even check whether it's going to be functional. So this is pretty bad, right? So well-definedness is a semantic condition that is hard or even impossible to check in general if you go to rich domains. Oops. So what can we do? So our goal is to capture capture a way to guarantee that spec is functional. Okay? So in order to do that, we capture the information that a stream may depend on. So that's what a dependency graph is. So in the dependency graph, it's a weighted multi-graph. The example will clarify. So the nodes in the graph are the variables in your spec. And the edges, you have an edge if you're using one stream in the defining equation of the given stream. So there is an edge from Si into blah if blah occurs in the expression defining Si. So if T occurs inside EI, then you have an edge between Si and T with weight 0 if you have no shifts, if you use the variable directly as a term. If you have shifts, then you have also edges, but in this case of weight k. If you think about it, this captures the dependency of whether a stream variable depends on another one, and what's the shift that you need to get to the other variable. All right, so for example, if you have this specification, we can check everything, but for example here S1 uses S2 with a shift of 1. So S2 with a shift of 1. This is actually wrong. We should have a +1 here, but this -1 is in this case these 2. Oh, S2 is 1 here, sorry. It's correct. Meaning S2 is used in S1 with offset 1. That's this edge. S2 is used in S1 with an offset -1. This is this -1. S2 is used with 0. That's the one that's, no, it's correct. It's here, S1, S2 with an offset 0. You have this. All right? So this is capturing whether you may need, in order to evaluate S1, S2 with a given shift. Now, another definition, specification is well-formed if the dependency graph has no crosswalks of 0 weight. First, let's think what this means. So a closed walk means that you may need yourself in order to evaluate yourself in a given point at the given point you're evaluating. This is the dangerous recursion. In order to determine whether S is true, I may need to know the value of S. Okay? So if you have no crosswalks, then you don't need yourself. You may need other stuff, but you never need yourself. Right? And therefore, we will see that you can guarantee well-formedness by that syntactic check. Well, how to check this property? Well, this is way much easier. First of all the domains have vanished. You only have the dependencies with what you need to fetch. Right? How do you check it? This is simple graph theory. So closed walks, the problem is that they're infinitely many because you're on the same simple cycles. You're saying any cycle. So you may go repetitively through a node. In principle, there are infinitely many candidates to be closed walks. However, it's enough if you check simple cycles, of which you obviously have finitely many, because you don't repeat a node in a cycle, right? So, fact, you have a closed walk of 0 weight if and only if there is a simple non-negative cycle and a simple non-positive cycle. If you have a cycle of weight 0 that is simple, you obviously have a cycle of weight 0. If you happen to have a positive and a negative, you can go through the positive some number of times, then through the negative the corresponding number of times that makes the addition 0. Remember that the weights are integers, so you can always do that. Are you with me? So I can build a complex cycle of weight 0 by repeating first the positives, say, then the negatives. So these two are equivalent, and this one can be effectively checked very easily. You just, if you want, enumerate all simple cycles of every given node, and then check. It's polynomial, obviously. Okay, so to decide well-formedness, you just check the existence of simple cycles. So there may be simple cycles, but all the simple cycles for a given node must be either strictly positive or strictly negative. All of them of one kind, or all of them of the other kind. All right? Yeah. Okay. This is what I just said. Well, this is strongly property, but it's implied immediately. So if you have a dependency graph and you take a strongly connected component, all the cycles in that component are either strictly positive, or all the cycles in that component are either strictly negative. A strongly connected component is a component in the graph that every node reaches every other node. Right? So your graph is composed by components, if it's well-formed, such that every component is either strictly negative, every other component may be strictly negative, and between components you have a DAG. Right? This must be intuitive. All right. Now, a different notion is the evaluation graph. So given an n, the evaluation graph doesn't have one node per stream variable, but one node per stream variable and position. So you populate your stream variable with the positions. So if you have a stream variable, for every position, you have a different node. You have the node of the variable at position 1, the node of the variable at position 2, the node of the variable at position 3, and so on and so forth. And now you populate the edges without any weight. You populate the edges between one position variable to another position variable. If this u is used in the defining equation of S, with weight 0, meaning it appears directly, and with k plus j, if this occurs in E. Obviously, k plus j must be within the range 1 to n, because this is a variable of the graph you're defining. Question. What are the outgoing edges of the variables of type input? Come on, raise me, help. There is none, because to begin with, it has no defining equation. And in order to add an edge, you must have a defining equation such that blah, blah, blah. Right? So the instances of output nodes are always sinks. Okay? They don't need anything. They don't depend on anything. This is actually capturing what you may need to evaluate SK in practice in an input without knowing the input. This gives you an over approximation of what you may need to compute. So if you have everything on the other side of the edge as a value, then you can compute that, for sure. You may need less, but with that information, you can compute. Right? So let me give an example to clarify. Consider this specification, which is, I believe, once t, right? Yes. The dependency graph is like this. So S may depend on itself in the previous position and on t in this position. T is an input. It doesn't depend on anything. I can evaluate t just by reading it. So the evaluation graph for size 7 is this graph. Right? Now, very nice graph. Particularly, it has one super nice property. It has no cycles. Right? Every instantiation of this graph will have no cycles. Yes, Elias. No, you don't. I'm building a mathematical object. Given an n, I have this. Namely, I have an infinite family of evaluation graphs for a given specification, one for each size. I'm not going to use algorithmically a computation of n. I'm going to prove mathematically that for every n, the evaluation graph blah, 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 if my dependency graph has a certain property, particularly well-formedness. Just wait. So I'm not intended to give a construction, an algorithm that calculates n and does blah, blah, blah. So, okay, in other terms, if I give you an observation of length 100, then you know that the graph is G100. Okay? But the theorem I will prove is that for any size, for any input, the graph will have no cycles. And that guarantees that all values can be computed in any size. Did I answer your question? So let's move on, and maybe you can ask later. All right. The connection between evaluation graph and dependency graph is the following. You have a specification and dependency graph, and you have an evaluation graph for some length, for any length. If the evaluation graph has a cycle, then the dependency graph has a zero-weight closed walk. If you remember, well-formed means that you don't have any of those. Therefore, the contrapositive tells you that if your graph is well-formed, which you can check, then for no size whatsoever, your evaluation graph will have a cycle. Right? You should buy, if you buy the lemma, you should buy the explanation I'm giving. Yeah, well, the proof goes graph theoretically exploring for an arbitrary n the relation between a closed walk and the walks in the corresponding dependency graph. Okay. And this is a corollary that I was telling you. If G is well-formed, then for every n, Gn has no cycles. So we just need one missing piece in all this theoretical development. Oh, just a second. Yeah, which is a connection between the evaluation models and the evaluation graph. Yeah. So give me a spec and give me only the streams of the input. Only the inputs, not the outputs. If my evaluation node for the length of the inputs, for an arbitrary one, has no cycles, then my specification has a unique filling here that extends the input. How do I prove that? Well, I have the Gn, it has no cycles, I can use the principle of mathematical induction. Right? Every element in my evaluation graph, which corresponds to one of the candidate values in these sigmas, has only finitely many stuff that it depends on. Right? So I can go inductively computing those values to the only possible value there is for them. For example, in the extreme case, you will have, well, you have the t's, then you have the s's, that the positions in the stream and the output streams that only depends on the inputs. Then those that only depends on those that only depends on the inputs, and so on. And of course, there is an upper bound because this is finite for any n. Right? So I'm just proving, I'm not saying how to do it efficiently or anything like that. I'm just saying that there is a unique evaluation model. So well-formedness implies well-definedness. This is undesirable, desirable, but undecidable. And this is checkable, and it implies what I want. In practice, take home message, write well-formed specifications, which is what every people in their own mind writes. In particular, all unfoldings of LTL, of course, are well-formed. Right? All right. The converse is not true, because just to begin with, we sketched that well-defined is undesirable, the well-formed is desirable. I mean, it cannot be the case, right? Because then we could check it is an undesirable problem, just to begin with. But I can give you a specification. So take this one. Is it well-formed? Some candidate. Think of the dependency graph. Whoop, sorry. S1 requires S2, and S2 requires S1 with an offset of 0. All the red flags in your mind should be, if you are programming recursion and so on, should be up now. This looks dangerous. So it's not well-formed, right? S1 depends on S2 now, S2 depends on S1. It's unlikely that I can do anything useful here, right? But in this case, you can, because look, this is a tautology. This is just a stupid equivalence to true that I just wrote here. So in fact, this specification on this line is just S1 equals T. And therefore, I don't have the dependency from S1 to S2. This goes away. So in fact, in reality, I have no cyclic dependencies. So this is kind of well-formed if I were to perform this substitution or replacement, right? Bottom line, this specification is not well-formed, but it's well-defined. Bottom line again, when you write runtime verification specifications write well-formed specifications for two reasons. One, because you want to have semantics. Two, because your compiler will reject them. Will say, error, your specification is not well-formed, no guarantees here, and then it will generate no monitor. Okay? All right. Are we doing in time? No? Yeah, we're okay. All right, so how do we do online runtime verification? This is what you all have been waiting for, because so far I just did mathematics, wonderful, beautiful mathematics, but no way to construct any monitor or anything. How do you do that? Well, the notational semantics guarantee only one output. Well-formed implies well-defined. If you write well-formed specification, you have one output. What do you do? Well, one way is that you wait for the trace, and then you enumerate all candidates and check. You know there is one. Well, you cannot do that for integers, so there must be a better way to do this. So the algorithm that we propose work on instantiating the variables to position variables as in the evaluation graph. So it's building the evaluation graph on the fly. So once you have this equation and you reach position k, you instantiate to this equation where the instantiation of the expression is the obvious one. So the constants are just the constants, the functions go homomorphically, and the shifts go to the shifted variables, which actually may not exist if you talk about the future. So this is the only tricky case, because you introduce new variables that may not exist in the system yet. And then you maintain two storages. So one is the storage of resolved equations, and the other is the storage of unresolved equations. So in the store of resolved equations, you have pairs of instantiated variable with its value. Obviously, for the inputs, you always have resolved equations. If you have processed the input all the way to k, potentially in the resolved, you have all equations of this kind for all positions up to k. Now, for the others, you may or may not have them. So you may have them unresolved, meaning that you have the pair that now the right-hand side is not a value, but it's a more complex term. In fact, a term that you have obtained by instantiating the defining equation, right? So this is just the two data types that your online algorithm will maintain. Now, what you do in step K is you add what you read from the input to the result. You add the instantiation of the equations to the unresolved, and then you try hard to determine the values of the unresolved. How? Well, by substituting everything that you have in all the right-hand sides of what you have in unresolved. Then you apply the functions if you happen to have the values, obviously. And then you apply simplifiers. Clever trick here, because maybe you don't have all the values, but you can still determine, right? Now, yeah, after doing this exhaustively, fixed point, very simple, you obtain that something in the unresolved has been resolved. Then you move it to resolve, and then you repeat. Of course, this terminates. It doesn't matter on the domain, because you're just making simpler terms, and your collection of terms is finite. So the only thing that can be happening in this loop is that you take a piece of your term, and you substitute it with a value, right? Since you have finitely many terms and finitely many pairs, this has to terminate, right? All right. That's one of the things they can do, but typically the way I see some, simplifiers is more like partial evaluation if you want. Sometimes by knowing a little bit of the inputs, you can determine the value of the function. Think in terms of partial evaluation. But the simplifiers I've seen in use so far are really simple stuff, like if then else with true values and Boolean simplifications, and maybe a simple integer computations, things like this. Potentially you could use solvers, but I mean, I don't think that the idea here is to use sophisticated simplifiers, but effective and fast simplifiers. All right. So one question is, can R be pruned? So for how long do you need a value in R? Because in principle, this keeps growing and growing and growing. Imagine that you're lucky and you resolve everything all the time. Your R will have all the values for the input streams and all the values for the output streams from the beginning of the computation to the current position. And you don't want that. Because one of the purposes that we want here is to do it efficiently. So we want to generate, if possible, monitors that guaranteed only use finite memory. And this is definitely not finite, right? So can R be pruned? Well, one important definition here, just by looking at the graph, you can compute for a given node all the nodes that depend on it negatively, directly, without any transitivity. So this essentially requires looking at the string variables u and checking whether v appears as an offset of -k. And take the maximum, okay? What does that mean? It means that you know exactly when v may be used by all possible use, okay? So you know that after waiting for k steps, the variable will not be used because it will have to be used already because u will have to be will have been instantiated. So at position k, this term in the result can be removed, will not be needed. If it had been needed, it would have been applied in the loop because the corresponding equation for u using it would have been introduced, would have been asked for vk, and vk would have been used. Are you with me? It's a bit tricky because maybe vk equals c is actually resolved and known after this position. What I'm saying is once you resolve this and apply it to simplify all the stuff, and the instant k plus nabla v, or later, you can remove it. Okay? So let me go here and give you one example. So I give these inputs, and I'm going to run the online algorithm to compute these outputs. Note that I have future references here. This is just an equation on the values, but I have future reference here. This is, again, a response property. So before pruning, the resolve and unresolved have the following. Let's go. So at the beginning, I read T1 and T2 at position 1, which happen to be false and true. That's simple. Now I evaluate S11, meaning S1 at position 1, and this happens to be, so this is true, this is false, false and something false, true and false, false, sorry, did I compute it wrong? This should be false, right? But in any case, it's resolved, because I have this value as false, and this value as true. Yes? No, come on. No. I'm computing what I receive up to here. Yes. Yes. This is the instance of input stream T1 at position 1. The instance of T2 at position 1. So these are these guys at position 1. And this is the instance of S1 at position 1, and this is the instance of S2 at position 1. Note how in this unresolved, I'm instantiating a variable that doesn't exist yet. So what I'm saying is S21, I don't know the value, but I know that is equal to the value of S22. That's what this equation, sorry, this should be a 1, 2, right? But it's the instantiation of this. Of course, if the trace were going to end here, I would use false here, and it will become resolved. Right? Now, the nabla that I said tells you that here, nothing depends on nothing else in the past. So everything is present or future. So as long as you resolve something in one, you can throw it away. So that's what I say before pruning, because what actually happens at the end of the online algorithm is that you end up with this guy and empty result. Nothing in here will ever be used or needed. Okay? But unfortunately, we don't know S21 here, because it depends on S1, 2. It depends on the next step, and we don't know that. All right. So if you can keep moving, at the end of the trace, you obviously resolve this guy, because you substitute by false S2, 4, and that allows you to resolve everything recursively. I don't have time to run all the examples, but I hope you get the idea. So my online algorithm, since I'm talking about the future, may take some time to tell me the value of a string variable at a given position. I'm not saying that it has clairvoyance. I'm saying that it knows for how long to wait, which may be the whole trace. But I mean, come on. This is a response property. You need to wait to the end of the trace to determine the value of the LTL property. All right? All right. So what's the worst case memory requirement of an online algorithm? Because you see, there is stuff unresolved that can keep growing. All right, so consider this input. I have references here that fall off to the end of the trace, as you can see here, and you use it in the else. So if you run this example, you will notice that you cannot say anything about sigma 3 and 4, meaning S3 and S4, at the beginning until I reach the end. Because I don't know whether it's S2, which is just S1, which is false, 1 true, so this is last position only. See, S1 is always false. S2 is the same as S1 in the next position, except if I fall off is true. So S2 will only be true in the last position, right? Now, S2 is used here. So in the last position, it will use T2, and otherwise it will use S3. So if you run it, you realize that you only feel S3 at the end of the trace. It's a similar example as before because you have future references. So the bottom line is that you need memory linear to the size of the trace for this monitor, because it's a monitor that requires clairvoyance, right? In a very convoluted way. So you need to record the whole feature history in order to say the answer now. Say, for example, that my answer now is some statistic, the average of all the values that I will ever see. I obviously need to wait for them and store them somehow, right? So the bottom line here is that your monitors may need, in general, an amount of memory that is linear in the size of the trace. Do you need more? Obviously not, because you can, in linear size, record everything that happened, right? But this is pretty bad, to be honest. Imagine that you have like 1 trillion events, a petabyte of events. You may have to read all of them. So are we again on a dead end? This is all just nice theory, but useless theory. Well, I will defend that it isn't. And I will defend it by having two definitions. So the first one is the fun of a node is that the node in the evaluation graph that node may depend on. So that means that to know SK, I need to know these guys here. Of course, for a given n, this may be very big. This is the evaluation graph, okay? And then the latency for a node is the one that is further away, which again may be the end of the trace if you have future references. But we know that in the evaluation graph, once I know everything in the latency, I can evaluate the node. So this is almost giving me the arithmetic or the theory that I need to know to give a bound. Okay? So if your latency for a node takes you all the way to the end of the trace, you may need everything till the end of the trace. Right? So efficiently monitorability, we have already seen monitorability, which is well-definedness, implied by well-foundedness. Efficiently monitorability captures the specification that only require a constant amount of memory that doesn't depend on the length of the trace. This is the important notion, because this is what you want to implement. All right? So, for example, every request is followed by a grant before the trace ends. You can have it like this, which is not efficiently monitorable. Look at this guy. Eventually grant means that I eventually see a grant, so I need to explore potentially all the future of the trace. But you can also have it negatively. So there are specifications that you can write it not efficiently monitorable or efficiently monitorable. So what's the difference? How can we guarantee? By looking at the dependency graph, you can compute the maximum traverse that is positive from a given node. All right? If you have a cycle, that's the length of the cycle. But you know that the latency is bounded by that. In particular, if you only have If you have no positive weight cycles, you only have negative cycles, the only positive paths that you can have cannot be cycles, right? Are you with me? So a node may depend on another node in one step in the future, but you cannot have recursion because I'm starting with future bounded specifications. And therefore, the memory I need is linear in the spec, but it doesn't need, let me go here, but it doesn't need a memory depending on the length of the trace. Bottom line, if your specification only has negative offsets, very intuitive, then all the cycles in the dependency graph have to be negative. Or maybe there are no cycles, but there cannot be positive cycles because offsets are negative. So if every variable that you have in your specification only talks about the present or the past, you can monitor with finite memory. Well, in LTL, this is more or less well known. People started monitoring only past LTL, right? Because you can determine the values. So this is the same idea here. Let me summarize for a moment. Efficient monitorable is all the cycles are negative. Very efficient monitorable means all the offsets are negative. Obviously, that implies that all the cycles are negative. Maybe an example can help here. But I want to move to offline. Bottom line, if you want to monitor and you want to guarantee finite memory, your references must be to the present or the past, not require clairvoyance. Or not require cyclic clairvoyance. If you want, only a little bit of clairvoyance. So you can compute for how long you need to wait, that's a clairvoyance, to determine a value now. Are you with me? All right. So that's very good for online. How about offline? Of course, I can run the same algorithm if I have the dump, but I can do way much better in offline. So let me show you this technique. So this is an online monitor. You generate the spec, and you have your system, generate your traces, you spec your outputs. Now in offline, at runtime, you generate a dump trace that then you process. Okay? So I have the luxury of having the whole trace now. What can I do then? Well, I can do way better things because I can, for example, start from the end of the trace and go backwards, if that helps me. Or I can do multiple passes, one going forward, one going backwards, if that helps me. Okay? So the first notion here, the goal is to have offline algorithms that schedule passes that only require bounded memory in each pass. Of course, this work in progress, where you can do map reduce or stuff like that, but this is just assume that the dump is huge but not humongous. Okay, so you can afford to do it in your computer. So the first notion, which is quite trivial, is you reverse everything. So the pluses are minuses, minuses are pluses, the future dependencies are the present dependencies. If you have the dump, there's nothing about the next. That is not about the previous. This is finite state traces. So I can have the same notion of efficiently, very efficiently monitorability for reverse efficiently, very efficiently monitorability. Okay? What would be those that you prefer to go backwards? Those where you only talk about the future. In the same way, that those that you prefer to go forward online is those that you only talk about the present or the past. Right? So the technique, this is the same specifications I had before. Obviously, the one that only talks about the future that was not efficiently monitorable is reverse efficiently monitorable and the other way around. So depending on the past, I would prefer this guy or that guy for the same specification. And we have the same notions of past bounded as future bounded, obviously. But now, the trick now is the following. You have the dependency graph is well-formed, because the previous takeaway message, well-formed implies well-defined, well-formed we can check. We only accept well-formed specs. So we have a well-formed spec, and as I said before, every strongly connected component, or every maximal strongly connected component, is either only positive in their cycles or only negative in their cycles. Otherwise, it wouldn't be well-formed. So what you have, let me go here, and an example. Say this example, is this well-formed? Let's look cycles. Positive, or let's better look at the strongly connected components. positive cycle, we're happy. So see that you have a negative edge, so it's not very, but it guarantees well-formedness because this is a positive component, this is a negative component, this is a positive component, this is a negative component. Okay? This offending -1 is ruling out the possibility that this is a very efficient graph, but it's an efficient graph in the sense it's positive in the sense of reverse. Okay, so the trick here is that we can schedule passes of this specification, of the specification that generates this graph, where we know how to resolve this guy either forward or backwards, and then use the values as the input for the next guy. So we can schedule passes on the dump trace that only require memory for the monitor linear in the size of the spec, independently of the length of the dump trace. How do you do that? You consider the graph of the strongly connected components, which is a DAG, right? Now, each of them is either positive or negative. So I hope I have done it properly. This guy doesn't have any cycles, but the others, I hope I've done it properly. Yep. Yes. And now you can schedule the passes in the following way. I start from the leaves. If it's negative, I go forward. That was an efficiently monitorable sub-spec. If it's plus, I go backwards. So I can schedule, and this is the algorithm I have here, I can schedule one pass here going forward, one pass here going backwards, one pass here going forward, and one pass here going backwards. In 4 passes, and obviously you can get that by the alternations of these guys, in 4 passes I can resolve my trace, 4 passes that do not require more than constant memory. Right? All right, and this is the algorithm. Okay, so I'm almost there. I have a few more material, but takeaway message. String runtime verification allows you to go to much richer formalisms, much richer domains with a more palatable language because it's almost a programming language. It has formal semantics. And you can schedule online and offline. You can know when you can do it efficiently, and you can schedule. There are many open problems, many interesting problems to work here. For example, one of them. It seems that this requires many different passes. Can I do it with less passes? Can I have a modified specification that only requires 2 passes, one forward and backwards? That's an open problem, which we only know for Booleans. For example, can I always, for the same spec, intuitive spec, LTL spec, can I have a efficiently monitorable, a reverse efficiently monitorable? Can I have it with only 2? Can I have future past or past future? What's the explosion in the size? We don't know that. So we know how to translate it into 2 passes only for the Booleans, and it's exponential. So this is what I do in these constructions. Let me go here, just the red boxes. I can translate NFA into Boolean string runtime verification with an exponentially lower bound, and the other direction, and this is the lower bound, and the other direction is linear. Yeah, okay, this is what I want to show. The decision problems are much harder than for NFA and LTL, which partly explains why this language is nice, because it's way more concise. So for example, language inclusion is exponential space hard. This is much, much worse than LTL, which is obviously p-space. It's implication, p-space, it's emptiness, right? So here I have an p-space emptiness problems, but all the other problems are much harder. All right, 3 minutes. We can afford. Extensions. I mean, all that I presented is more or less classical LTL with a little bit of syntax of modern Lola. But there have been extensions going on. So for example, one extension is what if you have specifications, or what do you have in your model, calls and returns, nested calls. What do you do then? You can use stacks as your type. That will take you a little bit there, but you can transform your algorithm of resolved and unresolved equations by adding to the syntax a different next in the trace going one step, and next jumping from call to return. And you can use a little bit cleverly stacks in your resolve and unresolved equations and have the same results. Meaning if you only use minus and minus in the abstract sense, you can do it with bounded memory. Okay? But I don't have time to explain the details. Recently in the finite group, they have extended LOLA with parameterized. This is something that was long missed because it seems like an obvious addition to go to quantified automata, but in this context. So I don't have much time to explain it, but essentially what they have is a way to instantiate an output stream for the member of the possible universe of inputs, which in this case is huge or even infinite, if you consider ideal integers, for the integers that you actually see. So for every different product ID, you get a different instance of this spec, roughly speaking. Another addition that they have more modernly is windows to compute these values, but I don't want to get there. So essentially, they can have quantified event automata, so to speak, in the stream world. All right. And then another addition that we have been working with the Tesla group and also independently is for real time. And this is much more complicated than it sounds because now your events don't have to be synchronous. Two sources of inputs can have the events in completely different places. So this is what I want to show here. Maybe you have an event in input E here, 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 there, but maybe not here. And this separation can be 1 millisecond here and maybe 1 day here. So this is more complicated because what do you mean by -1? -1 in where, in which stream? But this is way more complicated. So the first solution in Tesla was to use a bunch of building blocks and forbid time, particularly arithmetic of time. The second solution was to have richer blocks and controlled recursion, still no time. But the solution that Felipe has been working on is to use explicit time. All right. By removing the -1 or the -k and having a previous operator. So let me show, for example, one example here. So the stream X is defined in terms of the stream S of any type. So the first thing you need to do is when my stream that I'm defining ticks. Because before, it was trivial. It was ticking in all positions. It was synchronous. Now it's asynchronous. So the stream I'm defining ticks whenever the input stream ticks, and I want it to tick in 0. And the value I say in 0 is this value here, else is the value of the stream that they gave me. So this is a reinitialization of a given stream. I'm guaranteed to only evaluate these guys in solutions of these equations. So essentially, I unfold or I duplicate the equations to compute when I tick and to compute the value when I tick. It's a bit more complicated than this, but I hope you get the idea. You can have things, for example, I create a tick that ticks when the input ticks, but the values are not the values of the input, but the times of which the input ticks. And I do that by just plugging t here, right? So the type of the stream I'm defining is time. It ticks when the input stream ticks, but the values are changed. I can do things like that. I can do things like lifting. This is an interesting one. I have streams R and S of types T1 and T2. And I have a function from T1, T2 into T. This function doesn't know anything about streams, doesn't know anything about synchronous. Asynchronous is just a mathematical interpreted function. For example, addition. I have stream of integers, and I'm computing the addition. When do I tick? Well, I tick when something changes in one of my inputs. Otherwise, I'm giving the same value. So I tick in the union, right? And then what I do is fetch the value of one stream and the value of the other stream at the positions where they ticked previously, which could be this one, because this is a union, or could be earlier. I fetch those values, and then I compute the function f, which only knows about values, but these are values, right? And then I compute f. So if you want to imagine the functions, whenever one of them changes values, my defined function lift changes values as well. So these three were not given out of the blue. This is in Tesla 2.0 in the language modification of LoRa for asynchronous, which we call striver. This is the equations that you would write. And we can implement this, all the Tesla constructors and many other stuff, but this is work in progress. So I think I abused a little bit your time, so I want to leave it here. I hope I gave you an idea of what stream runtime verification is and maybe a deeper idea of the classical synchronous setting. So I can take questions now.